So I want to give you guys a couple of minutes on your own first. This area model that's on the left, so this one right here, this one is showing us this side of the equation. This is showing x plus 2 times y plus 2. The other area model, this one right here, that's showing us the other side of this equation, x squared plus 4. Or sorry, xy, not x squared, xy plus 4. What our task is right now, what I want to set you guys on for a couple of minutes and then we'll come together and talk about it. We want to try to figure out what are the numbers that should go in for x and y so that these two things are actually equal, so that they're describing the same amount of area. I'm going to give you guys about 5 minutes to look at this. You can substitute some numbers in. Whatever number you substitute in for x, it has to go in both x's. Whatever number you substitute in for y, it has to go in both y's. But we want the area model on the left and the area model on the right to come out to have the exact same total area so that these two are equal. I'm going to give you about 5 minutes to play around with it on your own. So have we tried anything in the place of x and y?
See, look, I'm gonna be honest with you. I did 5 before, and
Okay.
that totally didn't work. But I figured out the answer, but I didn't take care of that.
All right, well, let's talk about it. You said you tried 5 and 4 at first. So if we do 5 and 4, what's the area of this space right here? 20. What would be the area of this space right here? 8. What about here? 10. And here? 4. So if I wanted to know the total area for this one, I need to add up all those pieces, right? So I take 20 plus 8 plus 10 plus 4. What would that give me? 42. When I look at the other area model, I need it to come out to be the same if these are the right values for x and y. What would the area of this be? 20. And here? 4. So what would the area of this one be? 24. Same area? No. Is anything about them the same?
Yeah.
Yes. What would be the same? The 2 squared, so the 4 is the same, right? What else is the same?
20.
The 20 is the same. If we could just figure out how to get rid of the 10 and the 8, they would have the same area, right? How can I mathematically get rid of the 10 and the 8? I could subtract them, but I'm looking at the area here, so I need these areas to kind of just disappear. If these areas could just go away. So I don't want to get rid of an area that's there. That's what I can do with addition and subtraction, right? I need it to just not exist. What could I do? Think about area. How do you find area again? Length times width. So I'm going to multiply a length and a width together. And I want the answer to just poof, not happen. What kind of area would I be okay with there? If I want it to just go away, I don't want to deal with it. What did you say? if this area was 0, that would be super convenient, right? Would that be enough right there? What else would I need? Another 0, where? In place of the 10, I want that to be a 0. If I could do that, would my areas be the same? Well, how can I do that? It tells me that for sure this right here is 2. So how can I do length times width and get a 0 right here? If I make x and y 0, let's try that. So I'm going to make this 0. I'm going to make this 0. What would the area of this space be then? 0. And 0 times 2, I'd get 0. 2 times 0, I'd get 0. So the area of the whole thing would be what? The whole thing altogether? 4. Because I would have 0 plus 0 plus 0 plus 4. And I'd have a total area of 4, right? Talk to me about the other diagram. If I have to put the same thing in for x and y here. So what would the area of this space be? 0. So what would the area of this entire model be? 4. I'd have 0 plus 4, and I would get 4. Does the total final area for both of these models match? Is it the same? Yep. Yes. This really is equal now. 4 equals 4. Did this work with the first 2 numbers we tried? When we put 5 in for x and 4 in for y, did they come out to have the same area? No. Did we find any values for x and y that make them come out to have the same area? What values for x, what values for y? 0 and 0. We would say that this is a sometimes true equation. Sometimes true. Why? Because if x is 0 and y is 0, then the two sides are equal. But if we use different values for x and y, then they're not equal. What do you think it would mean for an equation to be always true? You can put any number in for your variable or variables. You guys have actually worked with always true equations before. Do you remember in Algebra 1 and Algebra 2, if you solve a system and you get infinitely many solutions? That's an always true situation. This is exactly the same thing as infinitely many solutions. And I don't have enough room to write that word all the way out. What do you think it would mean for an equation to be never true? What do you think that would mean? Always true doesn't mean that no matter what you put in, it works. Never true would mean nothing you put in works. This is the same thing as a no solutions problem.
Wouldn't that be like 5 is equals to 4?
Yes. Five equals 4, never true. Never, ever true. It doesn't matter what you put in for x. If you have an equation that has x's, but when you try to get them to the same side, they cancel out, and you're left with something that's not true, that would be a never true. If you have equations that have x's, and you try to get your x's to the same side, and you end up with things like 5 equals 5, that's always true. It doesn't matter what you put in for x, it's always going to come out to be something that's equal. An identity is an equation that is always true. An identity is an equation that is always true. Do you guys remember the other day how we were working with the properties of algebra to try to make one equation look just like another one? If I can make an equation look just like another one, it is an identity. They would always have the same answers because really they're the same equation. They just look different. But if I can manipulate them using the addition property of equality or the division property of equality to make them look the same, that is an identity. I'm going to put you guys into partner groups, and I'm going to give you sets of equations, kind of like what's up on top there. And I want you guys to sort them into 3 groups. A group for always true, the identities. A group that's never true, so there's no solutions no matter what you do. And a group of sometimes true. Remember, sometimes true means you can find a value. You're like, x equals this. But if you put in any other number for x, it's no longer true. All right, so I'm going to put you guys in those groups. You're going to sort them into those 3 piles. I want you guys to record these. Pay attention to the cards first, but then I do want you to record them in your book. Pages 113 and 114 have space for you to record your sometimes, always, nevers. As you guys are working through these, there is a check on our class Canvas page for today. There's a link there. So when you think you've got your groups put together correctly, you should hop into Desmos and check them. It'll tell you whether or not you have things matched correctly there.
Like we did that one time?
Huh?
Like we did that one time?
Yes.
Beginning of the year?
Yep. All right, so here's my groups. Taylor, you're going to work with Cheyenne.
Who's that?
You're Cheyenne.
I didn't say what it is.
That was pretty fantastic right there, I just gotta say. Edgar, you're gonna work with Min. Kyla Holmes, you are gonna work with Gianna. You guys need to be together because I'm gonna hand you a set of cards. So if you're not sitting near each other, you guys need to get up and move near the other person, okay?
Yeah.
Niles, you're gonna work with Nasiba. Dante, you're going to work with Sophie. Azina, you're going to work with Kaliha. Owen, you're going to work with AB. Who does not have partners yet? Brittany, you don't have a partner. Tanisha, Jocelyn, and Audra. Oh, Anastasia. Brittany, Anastasia, and Jocelyn and Tanisha. Hi, Stacy. Maybe you guys are on this lane. I'm gonna bring you guys your sets of cards. There we go. Need some more of these, and some of my paper clips are coming off. There you go. Set there. Go. You're welcome. So you can contribute. Put your head down. Slowly. Have your cards. Decide if you put in your cards. You guys are all. You guys are. There we go. All right, does every group have a set of cards now? Awesome. Okay. All right, guys, we only have just a couple minutes until the bell, so here's what I want you to do. Whether you're using Desmos or whether you're focused mainly on the cards, I want you to look at the groups that you have and take a picture of it. Desmos won't save where you're at, so take a picture of the screen if you're using Desmos. If you've got the cards, put them in the groups where you're like, I know these. It's okay to not be done. We're going to keep going with this tomorrow, but I want you to take a picture of where you're at right now so that tomorrow you can pick up exactly where you left off, okay? We are going to continue to work with these tomorrow until you get all of them. And you not only know which group they belong in, but you are 100% confident in why they belong in that group. There is no new homework tonight. Test happens after break, so I promise we will spend a little bit of time reviewing after break. I know. One more day until break, guys.